So my presentation is to show the work we've done on the seismic microzonation of the Greater Montreal area. So it's kind of follow-up of what Darius was showing, what was done for Ottawa. Just as a recap, we're looking at seismic effects. If we look at earthquakes, we have a lot of side effects that can be associated with the event. We can have surface rupture, we can have slides, we can have amplification due to topography, we can have rock slides, we can have site amplification due to soil, or we can have liquefaction. So the things I'm going to talk about are mainly associated with site amplification due to soil, but it's important to remember that there's all these other effects that are important when we're talking about side effects associated with earthquakes. I'll mention a little bit some of the work we did on liquefaction, but really that's not the emphasis of my presentation. So just to recap a little bit why we're talking about seismic microzonation. Well, Montreal is in the East Coast, and the East Coast is a zone of moderate seismicity. Just kind of a schematic of some of the recent activity in terms of earthquakes over the last 100 years. So if we look at the distribution of these earthquakes, what we find is that we do have a lot of significant events. We had over the last 100 years approximately 40 earthquakes between magnitudes 4 and 5. Far between magnitudes 5 and 6, and at least one earthquake with a magnitude greater than 6. So we can have some fairly strong earthquakes. In terms of the activity closer to Montreal, so we're basically in the same situation than Ottawa. Most of the activity, and this is pretty recent, this is for a period from 2000 to 2009, we see that there's quite a bit of activity in this zone here, which is the western Quebec zone. So in terms of earthquake hazards, this is really the zone that dominates in terms of hazards for Montreal. Now, if we look at what happened closer to Montreal, we do have some significant events that have occurred over the years. So if we go to older records, so predating instrumentation, we do see that we have quite a few significant events. So these are not instrumented, but they've been measured with the intensity scale. So the intensity scale, we've had events of intensity 6 and up to 8. And the largest one being what we infer as being intensity 8 earthquake of 1732. So if we remember the intensity scale, this is a qualitative scale. And if we go to the major one here, which is the level 8 intensity, this is associated with an event where there will be general panic in the population. There will be considerable damage to the general building stock, and most of the non-structural elements are going to get damaged. So if we look at the historical records, what we find from that event, that the earthquake was widely felt over the region. So 1732, Montreal was a small city, and there were more than 300 houses that were damaged during the earthquake. Now, if we come to more recent activity close to Montreal, we've had some significant events that were felt. So if we go back to 1935, there was the Temiskaming earthquake, which was a magnitude 6.2. And if we look at the intensity scale, we see that Montreal is in the zone 4. So there wasn't really any significant damage, but the earthquake was widely felt in Montreal. And then in 1944, there was one that's a bit closer, magnitude 5.6, the Cornwall, Ontario, Messina, New York earthquake, magnitude 5.6. And in this case, Montreal is just at the border between an intensity 5 and 6. So we saw some damage, not extensive damage, but there was some damage associated with that earthquake. Now, in terms of the side effects, Darius has mentioned this earlier. So why we talk about side effects is that this is illustrated by what occurred during the Mexican earthquake of 1985, which was a magnitude 6.6 earthquake. And this was kind of a dramatic illustration of what can occur. So if we add some instruments close to where the earthquake occurred, the peak ground acceleration that was measured at that site was equal to 0.15 G. As we moved closer to Mexico City, this is the type of thing we'd anticipate, that there is a decrease in the amplitude of the motion and in terms also of the peak ground acceleration. But if we go to sites that were into the city over soft sediments, what we observe is that the actual peak ground acceleration that was observed at the location of the city exceeded what had been measured at close distance to the epicenter. So that's kind of emphasizes the effect that soft soil sediments can have a great impact on damage in an urban environment. Now, if you come closer to Montreal, so we had one significant event, the Sagging event, that was quite far from Montreal. So it was at a distance more than 300 kilometers from Montreal. So in terms of intensity, we're located, again, in a region where we don't expect a lot of damage. We only had an intensity 5, but it is remarkable, though, that we were 300 kilometers away. So it is quite a bit of site effects, if you want, or effects in Montreal, considering the distance. And there was one particular building where we did see some damage in Montreal, which is at a site where the old City Hall from Montreal East was located. And there was extensive damage to the masonry of that building, and a lot of debris was found on the front steps of the building. And interestingly enough, this building is located in the eastern part of Montreal, and at a site where we have a thick layer of clay. So the layer of clay at that site is about 17 meters, and this is the type of thing we would expect, amplification of soil movements in areas where we have thick, soft soil deposits. So this means that it is of interest in Montreal to look at the location of these types of deposits, because they can have an influence on the amount of damage that we can have across the island. I don't know why it says, whoops, sorry. I think I messed up. Okay, so why do we do microzonation? Well, there are several reasons for doing so. First, once we do the exercise of microzonation, we can identify zones where we will have critical infrastructure. So within the critical zones, we can identify the critical infrastructure such as hospitals, schools, and fire stations. We can also identify our critical lifelines in terms of bridges, tunnels, and water supply. Identify if we have industrial sites also located in these critical zones, and then evaluate the vulnerability of the buildings. We can use also the microzonation to develop earthquake scenario, and from those scenarios we can evaluate damage to buildings, economic losses, and societal consequences. Also, the microzonations gives us a better understanding of hazards, so this can guide us in building new construction, and also in retrofitting existing structures to mitigate hazards, damages. So in terms of the microzonation, the work that has been done was to look at the identification of the seismic amplification zones. So we've done a little bit like was done in Ottawa. We've looked at defining the microzonation in terms of the National Building Code of Canada classification. So based on the VS30, the shear wave velocity over the first 30 meters of depth at the site. And we've also looked at other means of doing the microzonation based on measurements of shear wave velocity, but also using information about the fundamental frequency of the soil deposits. We also started looking at the identification of potential soil instabilities. So we've done some work on liquefaction and a limited amount on slope instability. The work can also be done, it can also be used for inputs to shake maps, which have been presented in the presentations this morning. So the shake maps can be used in a scenario mode to look at what could occur in terms of various types of earthquakes at different distances from Montreal. Could also be used in an operational mode, as was shown also this morning. So if there would be an earthquake, then you could use the shake maps to identify zones which have probably been most affected during the earthquake. And this can be used for guiding inspections and interventions. So what are the inputs to the microzonation? First set of inputs are to determine what are the soil types at different locations and what are their properties, and then do some analysis to determine the soil response in terms of amplification, liquefaction, or slope stability. So in terms of soil types, the information that we had is first with respect to the type of soil deposits. We had access to several surface geology maps. We also had access at a database on borings. In this case, we had a database of 20,000 borings. There's more borings than that, but the ones that actually went down to bedrock, there was only about 20,000. And then we subdivided those borings into a subset where we had detailed information on soil layers that was reliable. And we identified about, well, over 2,000 boreholes where we had great confidence in the quality of data for soil layers. In terms of geotechnical properties at each site, what we're looking for was information about soil properties to standard tests like the SPT. We did also some measurements of shear wave velocities and also some measurements for the fundamental frequency. So the first piece of information we started with was the surface geology map. And this one shows the island of Montreal. And then to the north, we have the island of Laval. And then we did start doing a bit of work on the north shore. And we did also some work on the south shore. And the zones that are of interest are the ones that are shown in yellow and in purple, no, not purple, and blue. That are associated respectively with alluvial sand and marine clays. So when we started the study, we coupled this with some knowledge about the land use in Montreal. So what we wanted to look for to do our surveys where we anticipated that there would be a lot of soft soil deposits. And also we wanted to concentrate our survey in areas that were more highly developed in terms of infrastructures on the island of Montreal. So from this map, what we see, if we flip from back and forth, is that we have the region all here along the eastern and southern part of the island where we have a lot of clay and sand. So these regions are regions where we would expect a lot of side effects. So this includes port facilities for Montreal, some of the refineries. I mean, there used to be more refineries, but we still have a few. And then parts of downtown. So some parts of downtown are in, we have some soft soil deposits. And then on the plateau here, in this part of Montreal, we also have some. So, whoops. So, one more. So all the region here, the Port of Montreal, and then going into the downtown area and on this plateau area. The other type of information we had is there were a lot of cross-sections that had been done by the city for different types of projects throughout the island. So these were very interesting because then we get a very nicely detailed variation of the soil layers. And using these type of information, we decided to come up with a simplified representation of site conditions across the island by using what we call a four-layer model, where we have till, sand, clay, and then landfill on top. And then this is all underlain by the bedrock. So using the 20,000 borehole, we were able to come up with a very detailed map of depth to bedrock. So this is the map here showing that we can go up to depths of 30 meters. So it's not that deep in Montreal. The deepest parts for soft soil deposits are at the tip of the island and in some areas here where we used to have lakes on the island of Montreal and a little bit along the south part of the island. We also use some historical maps This is an old map from Montreal dating back to the 18th century. So this is old Montreal here. On this map, you can still see the where we had the wall around the old city. And then there were a system of rivers, and this part here is an old lake that has disappeared today. But it is an area where we have a lot of deep soft soil deposits. And for those who know Montreal, this is where we have the Turco interchange. So using the model and the data, we came up with a 3D soft soil deposit model for Montreal. So this shows the contour line of the first layer corresponding to the landfill. This is the second layer corresponding to the sand deposits. Then we have the clay, and then we have top of bedrock. So we complemented that information with field measurements. So Darius was showing this device earlier. So we used this device extensively in Montreal, again because we had the equipment, but also it was very quick to get data. Basically, Darius took 20 minutes. We did 10 minutes. We were quicker. But so the only thing you have to be careful for with this is they have to avoid taking measurements when there's large vibrations. So you try to avoid going during heavy traffic or going close to industrial sites. Cannot work when it rains or if it's too windy. So a lot of the measurements done downtown were done by students very late at night. But otherwise, it's a very quick and cheap way of getting data on the ambient, on the natural frequency of a salt deposit. And this is what this shows basically that integrates many years of measurements using this technique. So all the little blue dots indicates sites where we did this measurement. And these represent various campaigns. So where we have a very close spacing here is the first year when we did this. We were doing it on a very small scale. And then the following years, we decided to, because it was working so well, we decided to expand it to the island. And here, the grid of points is not too regular. The reason it's not too regular is that we kind of look at the surface geology map and try to go where we thought there would be more soft soil deposit. And also, we were trying to go close to where we had borehole data so that we could do some correlation with the type of soil and the measurements we were making. So we did some measurements on the south shore, Laval, Montreal, and a little bit now up north of Montreal. Barry showed this, so I'm not going to talk about this much, but this is the type of result that you get from this little machine. And what you're getting in type of information is this peak that identifies the natural frequency of the soil column. So if we plot all these results, this gives us the map of the natural, the predominant period associated with the soil column. And what we find is that there's a very good correlation in Montreal, at least with respect to the depth or the thickness of soft soil layers. If I just take the tip of the island where we have the deepest deposits, we have the depth to bedrock, we have the type of surface deposits, and when we map this with the natural frequency, we get very strong correlations. So in conclusion, this is a very efficient method. We can, and for Montreal at least, we think that we get reliable estimates of F0 because we don't have very thick deposits. And we get a good correlation with depth to bedrock. So we did other types of measurements. We did also the MASW, like was done in Ottawa. So this allows us to basically determine the profile of the shear wave velocity at a particular location. The only restriction here is that you need a very long line where you can put down your sensors. So typically we did this in parks in Montreal. So I think we did a total of 29 parks around Montreal where we could do the measurements. Again, we were guiding ourselves on the surface geology map to select the most appropriate one of these sites. And again, this shows some of the results you can get. You basically get profiles of the shear wave velocity as a function of depth. We did also some seismic refraction and some seismic reflection. So this, again, is the Minivibe from the Geological Survey of Canada. We didn't do as much as was done in Ottawa. We did 7.5 kilometers. And again, we selected these based on our knowledge about soft soil deposits. So we did some measurement on the eastern tip of the island along Notre Dame Street, getting close to the old Montreal. And then this is in Parc La Fontaine, where we have a lot of soft clays. And then this is the plateau where we have also soft soil deposits. And this is the type of information you're getting from that Minivibe. So you get basically a cross-section where you can get the average shear wave velocity as a function of depth. And you can also get the interval velocities as a function of depth. And then finally, we also had the downhole measurements. So combining that information, we came up with relationships for typical soil deposits in Montreal. So we're using the data from these various sources. We developed some correlations for the sand layer as a function of depth, for the clay, and then we did similarly for the fill and for the till. For till, we ended up not having a relationship as a function of depth. We just use a value with the values of uncertainty associated with it, because typically those are not very thick. And there was quite a bit of variability also in the properties of the tills. We did also a model for the to relate the VS30 with the measurement of the frequency using the HSVR method. And as was mentioned again this morning, this is an approximate way, but it is one way to get a quick estimate of VS30 at sites where you don't do measurements. So to come up with our microzonation, what we did is we integrated all that information. We used the information from the surface geology, the geotechnical database, the measurements we did for shear wave velocity, and also on the fundamental frequency. We complemented that with some 1D simulation at some sites where we had good borehole data. And then we integrated all that information to come up with our best estimate of the microzonation. So depending on where we are on the island, there were different levels of information that was available. If we don't have any data, there's one method that has been suggested by the USGS that's not very precise, based on topography, in order to determine a VS30 value. You can use a seismic survey. That would be the best source of information. Otherwise, if you have information on depth to bedrock, or if you have detailed borehole data, or HSVR measurements, it's possible using the correlations that we developed to get some estimate of the shear wave velocity. So this is one of the maps that we generated. So this one was initially derived using only the information, using the relationship that we developed between VS30 and the fundamental frequency. So this was done using data at about 2,600 sites. And if we compare that to the map that we have for the surface geology, we see that the zones where we have Class D soils are very well correlated to the zones that we had identified earlier, where we had a lot of clay and sand deposits. And this is the composite model. So this is the one that we feel might be the definite one for Montreal. So integrating all the information that I showed earlier. And again, we can see that there's quite a bit of correlation with the presence of clay deposits and sand deposits. So in terms of site amplification, the largest we can expect are going to be in these regions. So again, all the port facilities would be heavily solicited in case of an earthquake, getting into close to Old Montreal, getting a little bit into downtown Montreal. There's a zone. There's a zone also in the plateau. And then we're going to close to the Turco interchange and DG. And then we have some other spots in the western part of the island. So again, this has to be taken in combination. So to do some risk analysis, we combine this information with all the information with respect to buildings and built environment in Montreal. So we've done this study, but I'm not really have time to talk about it here today. We've done also some work using F0 and trying to estimate amplification based on 1D modeling. So this would be an alternative way of doing a microzonation that is not based strictly on the VS30. I just wanted to show you one slide. This is some of the work we've done from liquefaction. Again, what we see is that there's not many sites where there's potential for liquefaction in Montreal, but again, they are correlated with the zones that we identified earlier. We've also done some site-specific analysis. This shows the Turco interchange. So the objective of the microzonation is really to get a feel for the regional risk and doing some regional risk analysis. If we want to do some analysis for specific structures or infrastructures, it's always recommended to do site-specific analysis. This is an example of one that was done for the Turco interchange. Finally, I just wanted to mention that we have a small network of accelerometers in Montreal that was a collaboration with the Geological Survey of Canada. So we have those located close to the downtown part of Montreal. Some are located on the soft soil. Some are located in zones where we're much closer to bedrock. And these are the records that were measured during the Val des Bois earthquake in 2010. The level of the measurements is very close to the level of noise that you get in the instruments. So we didn't get much from that event, but I just wanted to illustrate that in the case of a larger event, then we do have some instruments in Montreal where we'll be able to evaluate side effects at those locations. So in conclusion, Montreal is located in a moderate seismic zone with potential for significant damage. Microzonation has been developed and is being expanded to the greater Montreal area, so we're starting to move off the island and north and south. Liquefaction map has also been produced, probably can be improved with future work. Microzonation has been used to perform seismic risk analysis for Montreal. And we're doing some ongoing work to do the same type of analysis now for the city of Laval. So thank you very much. And if you have any questions, I open.